Okay, so this video will cover the modern physics in video form. Go through this fairly quickly. So I think most of it is pretty self-explanatory from the other videos. So when we talk about relative motion, we want to talk about frames of reference. This is a big thing. This is like if you're in a car and it's moving, everything's moving the same speed as you. So your friend in the passenger seat, you perceive that they're not really moving, even though they are actually going the same speed as the car. And this is the idea of relative motion. So because you're both going 100 kilometers an hour, you're going 0 kilometers an hour relative to each other. Another good example is even though Earth is moving really quickly, we kind of perceive ourselves as standing still because everything around us is also moving exactly as fast. And we only notice the differences. So this is the idea of relative motion. Um, This is valid in what we call inertial frames of reference. Inertial frames of references are where frames is where you're not accelerating. So for example, when you have an inertial frame of reference, that would be like a car moving at a constant speed. We call that inertial. Non-inertial is when the acceleration is happening. So when you speed up in a car really fast, you kind of have things shift to the back of the car. That would be non-inertial. Oh, so another example, if you're going a constant rate, you're in an inertial frame. If you're accelerating, like say you brake and everything kind of pitches forward, that's non-inertial. The laws of Newtonian mechanics are only valid when you're in inertial frames of references. And observations made in any inertial frame of reference is equally valid. So as long as everything around you is moving and not accelerating, we can use any law of physics. But once we start accelerating, those equations we've been dealing with don't work so well. Now, Einstein's theory of relativity is very important, and it relates to this whole idea of relative motion. So Maxwell determined the speed of light as 3 times 10 to the 8 meters per second. But 3.8 times 10 to the meters per second relative to what? Einstein determined that the speed of light remains constant regardless of the motion of the observer. Now this is really different from how other things behave. So, when you're catching up to a car, so say two cars are on the highway, the one in front of you is going 100 and you're going 80, it seems like the car in front is moving away at 20 kilometers an hour. So that's relative motion. But light is different because it doesn't matter how fast you're going, light always goes at 3.0 times 10 to the 8 meters per second. So that's kind of a really big difference. Light does not follow this whole relativity thing, where it doesn't move, it isn't different relative to you. So he considered this idea that the speed of light is the same everywhere, and this had some interesting consequences on the universe. He considered the idea that if the speed of light didn't change, this would imply that observers in different frames of reference would observe reality differently. So one thought experiment was the concept of a fast-moving train where observers were on the train and standing beside the track. So when we talk about this observations from the train, and you should check out the other video because it's hard to talk about, but it's a good video that I've posted in the other section. But anyway, so the idea is even though both kind of people observe different realities, that means their actual reality is different. So the faster you go, that actually changes your reality, which means things that happen simultaneously in one frame of reference may not happen simultaneously in another. And this is an interesting idea that time is actually flexible. Time passes differently. So when we think of a clock ticking, that clock ticks differently depending on how fast you're going. And this fact that time is not constant was quite revolutionary. Previously, it was thought that time was the same for all observers. However, Einstein's ideas show that this is not true. Expanding on this theme is the idea that the passage of time can be predicted mathematically, and it's indeed based on your relative velocity to other observers. And the first one we're going to talk about is time dilation. This is the idea that the faster an object moves, the slower time will pass from the perspective of a stationary object. We look at this concept using the Pythagorean theorem. Einstein's thought experiment began by imagining a clock that functions by bouncing a particle of light, a photon, between two mirrors. We can imagine this clock is attached to a spaceship capable of moving at a very fast rate. So this is the ship when it's at rest, and the photons bounce back and forth. But when we go into motion, we find that the photon, it has to move up and down, but it kind of has to go forward at the same time. And this gives us a nice triangle to work with. So indeed, the light has to take a longer path when it's in motion compared to when it's stationary. So stationary is a short path, but when it's in motion, that's a long path. But because the speed of light doesn't change, this means we have to resolve this by saying that the time has changed. And that's the interesting revolution that Einstein proposed. And the equation that describes this is as follows. This is the time elapsed for the moving object. This is the time elapsed for the stationary object. The v here is the speed of the object, and the c squared is the speed of light. Basically what this equation is showing is the faster you go, the amount of time that passes increases. So what this means is that if a person's moving at a very fast, a speed close to light, less time will go by for that person. Now it's important to remember that that person will feel normal. Nothing weird will happen to that person, but compared to somebody stationary, you'll have a different perception of time. The person stationary will have a certain amount of time pass. The person moving will have a different amount of time pass, but they'll both feel normal. And we illustrated this with the twin paradox. So if you keep one person on Earth and the other flies away super fast and then turns around and comes back, the person who was on the spaceship would have aged less than the twin on Earth because time is passing slower on the spaceship relative to Earth. It seems strange, but it was backed up by experiment. An airplane was actually loaded up with clocks, synchronized, and that airplane flew as fast as possible. And when the airplane landed, the clocks were no longer in sync. So that shows that through experimental evidence, this mathematical equation actually does describe it. Basically, the idea is the faster you go, the slower time passes. So another effect that results from moving close to the speed of light is that the length of the object contracts. This is another consequence that results from the fact that the speed of light remains constant for all observers. So when you look at the d equals vt equation, if you can't change the v, the only thing that can change is the length or the distance, right? Because for a given time and a set velocity, the distance must change. And this is really weird because we're used to time being consistent and inflexible. And we're also used to distance being consistent and inflexible. But really, those are flexible. It's the velocity that becomes inflexible. Because when we approach the speed of light, we're running up against an absolute limit. Distance has, to an extent, that flexibility to be big or small, and time has that flexibility to be big or small, but velocity is the one that's actually the more inflexible one. Anyway, we do have a equation to explain length contraction, and we have the length of the object in motion is equal to its length at rest multiplied by the square root of 1 minus the velocity it's going squared divided by the speed of light squared. Often with these equations, we won't put in the numbers, like we won't put 3 times 10 to the 8, but we'll put like 1, set the speed of light as 1, and we'll put this as like 0.5 if we're going half the speed of light. Because it's a ratio, the numbers don't really matter, just the relationship does. And so the last thing we look at is relativistic momentum. And so another effect that results from moving at a speed close to the speed of light is that noticeably anyway, your momentum starts to increase. This can also be interpreted as the mass of the object increasing as you go faster. So the equation that describes this is that momentum is equal to mv, which you know, this is p equals mv, that's the normal momentum equation, but we apply this relativistic correction factor, which increases this number. And this indicates an object that has a mass more than 0 can never be accelerated past the speed of light. This is because the force needed to accelerate the object would have to keep increasing as the mass increases. So because the faster you go, the heavier you go, the more force you would need to accelerate the object. But again, the faster you get, the heavier you get. So as you approach the speed of light, something would need an infinite amount of force because it would get infinitely heavy. Now there's some homework questions associated with that to practice. And the last thing we're going to look at is mass related to energy. So if you look at the formula for kinetic energy, Ek equals half mv squared. We've dealt with this a lot. Now the issue with this is under Newtonian physics, if we increase the energy, we change the mass, but we also change the velocity. And to an extent, as long as you stay at slow speeds relative to the speed of light, it works exactly like that. As we put more energy in, the mass doesn't change, but the velocity gets faster. However, velocity cannot just keep increasing without limit. The limit, of course, is the speed of light. And because objects cannot be accelerated to a speed that exceeds the speed of light, the mass of an object increases. So we need to write this energy equation as something more appropriate. And so we get E equals, instead of mv squared, we have mc squared because the speed of light is our velocity. And if you'll notice, that's the pretty common E equals mc squared equation. Of course, we need to apply relativistic correction because as something moves, this mc squared gets larger and larger. And of course, when we're not moving, we're at rest or going slow compared to the speed of light, the equation is very simple, and we get that E equals mc squared. So now you know where E equals mc squared comes from. And it's something you knew for a long time now. It's the same as E equals mv squared. The half is not so important because this mass kind of becomes irrelevant. So E equals mc squared at rest. E equals mc squared divided by the square root of 1 minus the velocity squared divided by the speed of light squared. This is interesting because now we've got a conversion that energy and mass are actually not two different things, but they are in fact the same thing. We can convert energy into matter or mass. We can also change mass into energy. And this whole idea of changing mass into energy is the foundation of things like nuclear power or nuclear reactions. So you can always use the long form equation. Of course, when something's at rest, it's much simpler to use the E equals mc squared. And that is it. There's some homework associated on page 583, questions 5 and 6, and 584, question 2. And that is it for the course. And I hope you enjoyed it. I had a blast teaching it. And I hope you guys learned at least a few things. All right, study hard for the exam and make sure you let me know if there's any questions.